Yeah, thank you very much, Andre. And I'm happy to give a talk on diabetes simulation. Also, thanks for your attendance, also on behalf of my co-authors, Marto Gruner and Thomas Franco are also here, and Heiko Peuscher, who is from the Technical University of Ulm, and who collaborated also with us in the preparation of this publication and in the simulation topics. And just to give you a short overview of our lab, because you will also hear other people from our lab today, we are heavily focused on human action regulation and how people are regulating different resources. And today's talk is going to be focused on physical resources. So as you can see on this plan, there are many different types of resources we are looking at. You can see it even better when I close this. So many different resources, many different projects. And what we want to look today at are health resources, and especially the topic of physical health here.
Should
so
just proceed the slides for you?
Yeah, maybe because you always need to press it here.
Okay.
Physical resources, and we want to have a look. Click on the diabetes management. And click especially on the topic of diabetes simulation, and click especially diabetes simulation, and next click in automated insulin delivery systems. So just give me one moment to explain what diabetes is, really, really short. I think many people already know it. So you have, usually your body is able to produce insulin, a hormone that is important to regulate glucose levels in your body. So we're again at action regulation, at regulating resources. And when you have type 1 diabetes, your body is not able to produce those resources anymore, and therefore you have to give it externally by making injections, for example. And because that is a very complicated process, which also induces a lot of workload, people have developed automated insulin delivery, click, which basically works like this. You have a sensor that is able to sense your glucose level, for example, 189 milligram per deciliter, and an insulin pump that will then give you accordingly the level of insulin you needed to regulate your glucose level. That is not always that easy, click, because sometimes you do sport and then, for example, your insulin level can be lower and you only need, for example, 1 unit of insulin, click. But maybe you will not need insulin at all because your therapy goal is already fulfilled with what the sensor has sensed in your glucose levels, click. But when you then eat something, you still need some level of insulin. So you see physical activity, ingesting food, and your therapy goals can influence how to regulate this. And it's not always that easy. And while it is mostly automated, it can have some problems because you need to communicate with the system about what you're doing and eating and so on. So unfortunately, it still, click, can lead to a lot of confusion, stress, and overload, which means, click, that 30% and more of the people, for example, in this study, discontinue AID systems. So they're actively stopping to use the system, which is tragically because the system really improves their health usually. So they're way more healthy when using the system. And the number of people who are unsatisfied by the system is even higher. And there are some ideas what you can do. For example, click, you can make a training. Not works. Perfect. Thank you. You can make training so people can experience the system beforehand, learn to understand them and how to use them. And this is also what we want to talk about today, because we developed a simulation of automated insulin delivery that is also open source and can be used in training contexts. And we wanted to understand whether and how this can be a safe way to learn how to use automated insulin delivery systems. So what you can see here, I don't want to go too much into detail, but that is how you like modeling the physiology of a person. That's not even the AID system. That's just the body that is modeled here. And those models are typically very complex. You need a lot of technical knowledge to use them. For example, this is only implemented in MATLAB, or was only implemented in MATLAB. And there are many features that are important for everyday life, which are still missing. For example, physical activity or different types of meals. We implemented that in a very relaxed model that is like a regulatory loop, so control loop, where you have the sensors, you've seen them before, you have a controller, the insulin pump that acts like an actuator, and then you have the patient physiology that you have seen before. And we implemented that or Heiko and his colleagues implemented that in a web interface that looks like this. So this would have been a video where you would see that actually by changing those parameters or the settings here, you can change the curves of the glucose concentration over time. And this way you can experience how, for example, different sizes of meals will be adopted by the system in different ways. In our research, we wanted to understand what are features of a human-centered simulation of automated insulin delivery, because what you've seen on the slide before is not what a patient would like to use. So we conducted interviews with 12 persons, 3 physicians, 3 diabetes counselors, and 6 patients. And we wanted to understand what is their experience with AID systems, but also what functionalities they are expecting. And we conducted a thematic analysis, and in the end, we found 4 big themes, but I will bring you 5 of the requirements that we defined in the end. So the first one is they need an interactive individualization of parameters. Yeah, you have seen that already before. People want to see how the system reacts if you change the level of carbohydrates, or if you, for example, say, I do a lot of physical activity, or I am 20 pounds more or something. Yeah, and this is already something that we implemented, and you can also compare different settings. This, for example, is one curve where you have a meal of 30 grams of carbohydrates and the other one has 60 carbohydrates. People also want to have a real-time modification and feedback of parameters. So they want to immediately see how that affects the system, something that we could maybe see in this video. So if you're interested, you can later come to me and I can show you the video at my computer, because it is really possible here in this kind of simulation to change and then immediately see the effects. And also there's a feature integrated here where you can see old curves and you can like immediately compare them. And people want to have predefined scenarios. That is something very important that no literature has mentioned before. So they want to jump into a specific scenario that is important for them without having to adjust many parameters. So for example, going to the gym or after lunch or being on a long flight or after sleeping. So those are parameter configurations that they want to have predefined. They want to have every parameter that they can change to be explained, and they want those parameters to affect the insulin calculation and also an explanation of how this calculation in the end resulted by the AID algorithm. So what we did is we tried to convey that into one prototypical interface that we then implemented in the user study, and we did this here. I will just go shortly over what we have done. So you can see we already have those predefined scenarios. We have different parameters that you can adjust. You can hover over them. So it is described what they are and how they will affect the AID system. You can confirm your changes. You can directly skip to predefined scenarios. And overall, we have a few parameters that you can change, but not too many. Like the original model that you have seen before, you can change like over 120 parameters at all. But does that work, or do we have any advantage in using that? So the effects of a human-centered simulation of automated insulin delivery have been studied in a short, very small examination, but we had 4 hypotheses that we wanted to test. So first, the perceived traceability of how this intelligent system works is higher for an interactive simulation. And if you can just only observe screens, the trustworthiness is higher, the workload is lower for the interactive version, and the prediction accuracy, I want to speak later about that a bit more in detail, is also higher for the interactive version. To measure the traceability, something I want to highlight, we use the SIPA scale, which is a scale for subjective information processing awareness divided into 3 subcontracts: transparency, understandability, and predictability of the system, and that have been applied in the diabetes research already before, and that we also wanted to use here. This study consisted of 32 people, 62% were female, and they had a mean age of 63. And 20 of those people already had diabetes, and the remaining 12 people were like caregivers for somebody with diabetes. So they were all experienced with diabetes. And we had a within subject design where we compared a static and an interactive version. And the measures we used were the perceived trustworthiness facets of system trustworthiness scale, the FOST scale, the SIPA scale, the NASA TLX, and self-developed items for the prediction accuracy, where we said, okay, we are going to change this parameter. How will this influence the insulin demand calculation? Will it go up? Will it go down? Or will it remain the same? And we checked if people chose the correct answer or not. We had an initial questionnaire to understand how experienced people are with diabetes and to like sort out people who were like just faking to understand diabetes. And then we had a block with the static and one block with the interactive version. We depicted only images in the static block and then asked our variables. And in the interactive simulation, people were able to choose the parameters themselves. Both blocks were limited to exactly 5 minutes, and people were asked to like check pictures until 5 minutes are done or to explore until 5 minutes are done. So it were exact 5 minutes for both conditions. So what did we find? For the first hypothesis, it's a little bit mixed. So we found a significant effect for the predictability of the system, but we only see small effect sizes overall. So we can't really say that traceability is that much affected, but we can see a trend here, and 32 is not the largest sample size. So it would be interesting to have a replication maybe with a larger sample size to see whether the interactive version is really more predictable. For trustworthiness, we didn't find an effect. So the trustworthiness didn't differ. And I would like to speak about that in the discussion. But the workload in the interactive version was significantly lower. And here we find also a medium effect. And the same is also for the accuracy of the prediction. So people were way better in predicting what is happening in the system after using the interactive version. So what does that mean, and what is the future of human-centered simulation of AID systems? So we derived some guidelines that are close to our qualitative findings. It should be an interactive adaptation of parameters that is possible, a real-time feedback that can be done. The effects of user communication should be highlighted in demonstration, and scenarios should be typical or challenging situations for people with type 1 diabetes. And also users should be encouraged to use the situation in physiology they have, try to make assumptions about that and to generate hypotheses that they want to test. We had a few limitations. For example, we had a fixed sequence of the static and the interactive version where we maybe should have like mixed it up, but we assumed that the learning effect in the interactive version is way larger, what we also found here, but it could also be just a progression, yeah, also a linear effect of learning here. So there maybe should also be a between design to compare those different groups. And the functionality of the simulation was quite limited. So no physical activity was really taken into account, or only to a little amount, and also different meal times were not. So the low trustworthiness rating was not due to the type of interaction with the system, interactive or not, but due to the limitations of the underlying model that we didn't change. So that is, we assume, why we did not find any differences in the both types. So that's about safe environments to understand medical AI in the context of type 1 diabetes. Thank you very much for your attention, and I'm happy to hear your questions.